Hey, students, guess what time it is? It's science time. Get out your notes and let's start learning.
I miss you guys. I wish this was under better circumstances here, but guess what? We're starting a new chapter, and so we're going to start getting into circular and projectile motions. And so the first part we're going to start getting into is with projectile motions, which is a form of a curved path. So let's start off. When we start getting into projectiles, the one thing that you're going to realize is that right now you have all the information that you need. All we're doing is we're just taking some previous information and applying it in new situations. So it's really nothing new. We're kind of going back to the basics of with your different velocity and acceleration formulas, and then also getting back into vectors. And so kind of a combination of those in a new sort of way here. So a little bit of this is review, and let's get learning here. So dealing with the motion in a curved path here, projectiles fall at 9.8 meters per second squared. Again, that's nothing new here. So here on Earth, all objects close to the Earth, surface of the Earth, fall at a rate of 9.8 meters per second squared. So in other words, if it's going up, it's decelerating at negative 9.8. If it's falling back down, that's going to be a positive 9.8 meters per second squared. So yeah, that's one thing here. It's going to be the same thing as before. Also, projectiles move horizontally at a constant rate. And again, we're ignoring wind resistance. But ignoring wind resistance, all objects move at a constant velocity horizontally. So in other words, horizontally, as an object is moving across here, it's going to be moving at a constant rate as it goes across. But as an object is falling down, it starts off slow, it goes faster, and it goes faster. So we have basically those two types of motion here. So vertically, an object is going to be falling down faster. Horizontally, the object will be moving at a constant rate. So kind of think about like rolling a ball across a level floor. It moves at a constant rate. Again, ignoring friction or wind resistance. If you drop an object, it's going to be speeding up, speeding up, speeding up. Or even if you toss it up in the air, it's going to slow down and slow down and slow down, eventually come to a stop, and then it speeds up, and speeds up even more. Okay, so basically it's just a combination of those two things. So we're going to get into a little bit more details about that here in a moment. Okay, so let's move on. So solving projectile problems. If it's something that's happening at an angle, this is going back to resolving the vectors, and all we're doing is just solving for the x and y axis of it. So we had to find out the amount of time it will spin in the air, and that is due to this vertical component, in other words, this x and y component, and also to find how far it went, what they call the range of it. What we're going to be looking at is the horizontal velocity and the amount of time with that here. So again, with the projectile motion, if something's happening, so if you have a ball and it's moving at an angle, like so, come on now, okay, all we're doing here is we're taking this and we're breaking this down and to find its horizontal component, and also we're trying to solve for its vertical component. And so almost as good as what I draw on the marker board, huh? So if an object is traveling at a certain angle, it's both moving horizontally and it's also moving vertically. So this aspect of it here controls how long does it spin in the air. But then the amount of time it spends in the air is also the amount of time that it's traveling horizontally. So those two things here are going to determine how does this move here. So this is going to spend how much time in the air, and how much it spins in the air is also going to help determine what is its range, or what is this horizontal distance that it travels. All right. So Now, granted this is not Pixar, but if we have an object that is thrown upward at some angle, it's going to be moving something kind of like that. Again, kind of use your imagination, like tossing a ball. I can't exactly do that right now, but you get the gist of it here. I think one or two of you have thrown a ball once or twice here before. So again, when you throw a ball, it goes up, it reaches the highest point, and it comes back down. So it starts off over here, and comes over, and it's, use your imagination. So it goes over, reaches its highest point, and then it comes back down. Okay. So when you're looking at just a vertical component of it, when it goes up into the air, it goes up, reaches the highest point, and it falls back down. And again, this is not Pixar, so I apologize here, but let me back up here. So in other words, whether you toss a ball straight up in the air, if I toss this straight up in the air, this is just going to go up, pretend that's a straight line, reaches the highest point, and then it falls straight back down. Okay? So it goes up and goes back down. If you were to throw a ball at some angle, and you resolve this to its vertical component, let's say it has this type of vertical component to it, and if this object here also had the same vertical component, same velocity thrown upward here, what would happen then is that they would both reach the highest point at the same time and also come back down at the same time. So the two would be in sync to each other. So as it goes up, and then it ends up falling right back down. Okay. So it's kind of like if you ever are driving in a car, and if you're sitting stationary in a car, don't ever do this while you're driving here. But if you're a passenger in the car and you're tossing a ball straight up and down, even though you're moving in a car, maybe 50 miles an hour, you're tossing the ball straight up and down. To you, it looks like it's just going up and then coming back down. But someone from outside of the car watching this, they would have a different frame of reference with but the ball would be moving something like this. But the thing is, these two are actually the same motion. All right, now, if you look at this range, so if you throw a ball upward at some angle, and at the same time you roll a ball across the ground, what would happen here, again, this is not Pixar, but one thing that would happen here is it would actually stay underneath each other the entire time. And so, backing up, if I were to throw this at some angle in this direction here, and break it down into its horizontal component, velocity component here, and if this ball was to be rolled at the same velocity as this one over here, what would happen here is that they both would arrive at the same point at the same time. So kind of think about this, especially for some of you in some of the sports here where like baseball, softball, football, something like that, and you are, if you're throwing a ball at someone here, if the person is able to run fast enough and you're not throwing the ball super fast, it is possible to always be running underneath the ball, and the ball will go up, come back down, and the person running after the ball would be able to capture it. And unfortunately, I have a demo in the classroom that you guys are not currently at to see this, but it's kind of a neat thing here. But it's the same thing here too, that if you are just walking across on the ground and you're just tossing a ball up and down in the air, you would see, you don't have to throw in front of you. All you have to do is just toss it straight up in the air. Oops. And it would always land in your hand. The same is also true if you're dribbling a basketball. As you're dribbling the ball, it's actually a reverse throw. In other words, you're throwing it down, it bounces, it comes back up, and it always lands in your hand here. So in other words, instead of having, like if I'm walking and tossing a ball, it would look something like this. But if you're dribbling, let me draw it up here. If you're dribbling, it would actually look like this. Now, something kind of like it here. It's actually the same thing. So, something to kind of think about here. As you're dribbling a ball, it bounces on the floor, it comes back up, you push back down on it, but the thing is, you don't have to push it out in front of you. All you have to do is just push straight down on it. It still has the same horizontal velocity. It's always able to land back into your hand. So at this point here, to find out the range, in other words, if you're looking for the distance, the range, that's actually the distance in the x direction. We need to look at the velocity that's occurring in the x direction versus the amount of time. And the time is actually coming from the vertical component of the projectile. Amazing graphics, I know. I was like, wow, Mr. Souder, you're good. I know, seriously. Okay, so now, if we take both the horizontal and the vertical components and combine them together, so in other words, this ball, let's see, if I take this and I have this going up at some angle, and I break this down into its horizontal component and its vertical component, okay. So this ball would have the same vertical component, and this ball over here would have the same horizontal component. Okay, so this ball right here has these two combined. And so what we end up having here, in other words, if I take this vector, add it onto this ball, and I take this vector and I add it onto this ball at the same time, we end up getting a resulting vector. Amazing how that keeps coming back, doesn't it, huh? But, so when those two things happen, we end up having a motion like this, which basically means that, this thing will go up, starts off fast, and it slows down, and it slows down, and it slows down, and it comes to a stop. And then it's going to fall back down. It starts off slow, it speeds up, it speeds up, it speeds up, and then it goes the fastest here. Horizontally, it's kind of like a ball rolling across the ground. It travels at a constant velocity all the way through. It just moves along. Okay, and so that is the reason why when you combine these two together, these two at the same time, you end up getting this arcing path. Sometimes what they call like a ballistic path. So here's a graph that shows a projectile, three different projectiles actually, one at 0 meters per second, one being shot at 1 meter per second, the other one at 5 meters per second, if you shoot them horizontally. Now this one here basically would mean that the object is just being dropped. So if you're 120 meters up and you drop the object, at first increment of time will be here, the next increment of time will be here, the next one, and the final one here. But look at this. If you have a 1 meter per second, in other words, this one is now being, for this square one here, it has a 1 meter per second horizontal vector to it. So it's like shooting a gun straight out or flicking something right off of the edge of a table. And if it leaves the table at 1 meter per second, if you notice, these two are level because once it leaves the table, it's now under the influence of gravity. So as it goes down, it's always going to be the same. And if you look at the triangle shaped here, this is now being shot at 5 meters per second. And so every second, it's going to travel 5 meters horizontally, but vertically, look at this. vertically, they're all the same all the way across here. So that means an object being dropped versus an object that's being shot horizontally, they will both fall at the same rate. And that's, for anyone who does any form of shooting, you would notice that here that that after a certain distance, the object or the projectile will fall more and more. It's not quite like in cartoons here where you have a cliff and then all of a sudden, I don't know if anyone still watches the Roadrunner here, but you have the little character over here and they run off and all of a sudden they realize they're off the edge and they fall straight down. It's actually more realistically like that. So they're, if you run off of a diving board, you don't jump, but just run straight off, it will feel like you're doing this. But in reality, you're doing this. Now, look at the shape of this. Anyone recognize that? Anyone? Bueller? 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 Anyone know what shape that is? Come on now. I know you went. I know what it is. And I know someone out there knows it. Show of hands. Anyone? Good, good. I heard someone say it. It's called a parabola. Okay, that's a parabolic curve. Okay, and that's something that all projectiles follow a parabolic curve. Okay, that's one thing that I want you to keep in mind here is every single projectile follows a parabolic curve. Even something which is going straight up and down here. And basically it's a parabolic curve that's collapsed on itself. But something like this, it's a part of a parabolic curve. And this is the also a larger, wider parabolic curve. But all objects follow a parabolic curve. So all ballistics, if you hear like a ballistic missile, or technically a bullet is a this ballistic here, that all ballistics follow a parabolic curve. Okay. Now, this is one where it's a little bit harder to actually see what's going on with this. But this is a graph of an object that is being shot upward, but also has, some of these have a horizontal component. So in other words, for the, in this case here, for the triangle shaped one here, this one will be just as though you're tossing the object straight up in the air. It'll go up and it comes back down. It's kind of hard to tell because it's hard to differentiate between the up from the down. Okay, but if you look at the 5 meters per second, so if it has a horizontal velocity of 5 meters per second, like this, that means every second is going to be traveling. And if you look right here versus here, so it goes like half of the width of a line here. Here's another one. Here's another one. Here's another one. So it's a half, 5 meters per second, according to the scale here, is only about half the width of between the lines here, all the way down here. So horizontally, it's still the same. But if you look at vertically, it's going to go up, it's going to slow down, it's going to slow down, slow down, slow down, slow down, comes to a stop, and then it's going to start speeding up, speeding up, speeding up on the way back down. Okay? Or even if you look at the 10 meters per second one. So if you give it a higher horizontal velocity. So every second, so this would be 10 meters here. And then if you look at the next one here, it's 10 meters. So every line here is 10 meters. 10 meters, 10 meters. It's always traveling horizontally 10 meters. So the velocity is constant this way. But vertically, if you look starting from here, it traveled a large distance. And then it traveled a little bit less. And then from here to here, a little bit less. And from here to here, a little bit less. Reaches the highest point here. This is the, vertically speaking, it's not moving here, but still moving horizontally. And then it starts speeding up as it falls back down. And again, if you notice the shape of this, this is a parabolic curve. All right, so now, kind of showing it in a little bit different way. So if you have an object which is falling down here, so we're starting from here where the object is stationary or is being shot off at some angle, so just be like this initial velocity. So we can kind of say that this has a a certain horizontal velocity. Pretend that's horizontal. Okay. And as it takes off, as it begins to move here, you can look at the horizontal velocity and its vertical velocity. But if you combine these two, or its horizontal displacement and its vertical displacement. If you look at these two, this is actually the result of those two. You know, the next moment of time, let's say the next second, is now moved this far, but it's also dropped this far. Next second, it's traveled horizontally this way, and it's dropped down this far. And then when it's over here, it's traveled horizontally this far, but it's dropped vertically this far. And again, if you look at the horizontal components of it, they're all equally spaced. It travels horizontally at a constant rate. Vertically, the displacement gets larger and larger as it's accelerating downward. So it looks like a ball or some object being dropped. But if you take the horizontal displacement and the vertical displacement, you end up getting this shape. If I can draw the line here halfway decently, you will get a parabolic curve-ish. And again, if I put a vector into it, so this would be like a projectile running off of a table, or a projectile leaving a gun or a bow. And so initially it only has a horizontal velocity. Okay, but as soon as it leaves like a muzzle of a gun, gravity is going to take over. And so as soon as the first increment of time, you still have this horizontal velocity, but now you have a little tiny bit of a vertical velocity. And then as it goes on, you notice horizontal velocity remains the same. Vertical velocity vector here is increasing. And it's increasing some more, and it's increasing some more. But if you notice, this value right here did not change, but this one has. And so you end up getting, again, that parabolic curve. So this is a graph, again, kind of showing the same thing here, where we have an object that is a projectile following a parabolic curve. Okay, we see the horizontal velocity vector as it's going along. And if you notice, that matches the same thing with these down here. They still have the same horizontal velocity vectors. And if you draw a line straight down, they would all intersect at the same location. Now, this part here also has a vertical velocity, which also matches, though, like a ball being tossed straight up in the air. So it would go up, and then the velocity vector would be less, and the next moment of time velocity would be less, and then over here velocity would be less, and right here at the very top is where the velocity vector will be 0. And then this will be like if it's beginning to drop down, which is kind of the same thing that's happening with the second half of its path here, is that as it's going down, it starts off with no velocity vector vertically, then has a little bit more, and keeps increasing here. So in other words, if I take the horizontal velocity vector and a vertical velocity vector, combine those two together, I end up creating this, which then creates this resultant. And if I go to this one here, if I take this horizontal, combine it with this vertical velocity vector, combine these two, I end up getting this resultant. Now, here's something else to notice too. Look at the resulting vector and notice the path. How is it relative to the path? And all the way through, if you look at the resulting velocity vector versus the path that's traveling, even up here at the very top, even though it doesn't have a vertical velocity vector, so here's this velocity vector, but if you notice, there is a term for that. Does anyone remember that term? Anyone? Anyone? Show of hands. Come on, guys. I know what this is. Yeah, that's right. It's called tangent. This vector, the resulting vector, is tangent to the arc. And if you don't remember what tangent is, let me draw this out here. If you draw a circle, ooh, look at that. That's pretty nice. Tangent is where you take a line. I did not do so good on that one here. Pretend it's only touching on one point here. So in other words, if I take a circle and I take a flat board and lay it across here, it should only touch it at one point, okay? Now, if I try to draw it in the other way here, something like that, it's going to be intersecting the circle at two different points here, okay? So again, let me see if I can try to draw this again. Okay, no. Yeah, okay, something like that here, okay? So this would be tangent to the arc here. So at this point right here, because this is a curved path, if I draw at this point a line that runs tangent to it, that means if I draw a line like so, yeah, it's not too bad. This would be the point that is tangent to that arc. Okay, so this line is running tangent. In other words, if I extend that line straight back, it's only touching it right there. If I take this line and I draw it straight back, it's only touching that arc right there. If I take this line and I draw it straight back, it would actually leave the line and it's only touching that arc right there. It's not going to be crossing over it. It stays on the same side as it. All right. Oops. Didn't want that to happen. All right. So let's move on here. So this, again, I'm just trying to draw out that if you take the horizontal velocity vector and the vertical velocity vector, you end up getting this line here. This line would be tangent to this arc here. Now, what I've drawn here is not exactly perfect, but I try to make it a little bit more of a larger separation here. But if I extend this line straight back, it would never cross over to the other side of this line. And that's what tangent does here, is that it does not cross over to the other side here. So, and we're not doing something like this or something like that. That will not be tangent. Tangent would be something kind of like that, where it touches the circle at that one point right here and does not go over to the other side. That will not be tangent. All right. So again, if you look at the resultant, all the resultants are always going to be tangent to the arc, the tangent to the parabola. Okay. And again, just another diagram showing an object being dropped. Technically, a dropped object is still going to be tangent because if you have a vertical line, okay, let's see if I can draw a vertical line. So if I have a vertical line and I draw a line that's going to be tangent to that, that means it's going to lay, if I lay a flat line right on top of it, it's going to lay right on top of it. So even a dropped object is tangent to the path that it's traveling. So tangent, it was always a straight line pressed up against the path that it's traveling here. Or if there's a bend to the path that's traveling here, it's only going to be, it's a straight line that's touching that arc at one point. So I think you guys, hopefully you guys understand that. If not, send me an email. I'll try my best here. All right, so with this one here, again, you have an object. If it's moving across horizontally here, horizontally is going to be constant. Vertically, because under the influence of gravity here, it's going to be accelerating as it falls down. But something rolling across the ground, gravity does not work sideways. It only works vertically. So if they have an object moving across horizontally here, it's not going to be affected by the acceleration of gravity. Okay, now here's an old picture of a bomber, of course dropping the bombs here. A couple of things I want you to notice about this is that if you look at the bombs coming out of them, if you notice, they all are in a straight line. And the reason why is because this airplane has a certain horizontal velocity. And because these bombs were being carried by this airplane, every bomb will still have the same horizontal velocity. So every single one, okay, pretend that's one the same length as that one there, but they all have the same horizontal velocity. Okay, so that's the reason why they're all underneath the airplane. Now, something else to notice here too is look at the spacing in between them. Notice anything about that? You should notice here, between here and here, they're kind of close. Between here and here, they're a little bit further apart. It's kind of hard to tell, but this one are a little bit further apart, and this one's a little bit further apart as well. And what's happening here, because this is the last one to be dropped out, it has a little bit of a vertical velocity vector to it. This one has a larger one. This one has a little bit larger one. And it goes right down the line where this one has an even larger one. I can't draw the next one here, but so when it first dropped here, if there was a bomb up here, initially when it's dropped, it only has the horizontal, but it has no vertical. And that vertical vector will start increasing. And you start having these separation here. And that's one reason why if the plane does not change direction, it does not speed up or slow it down or change direction here, essentially the bombs will be exploding directly underneath the airplane. Now he's up awfully high here, but again, there's a factor that we don't, a lot of times in physics, we ignore. It's also wind resistance. And you can kind of tell a little bit more on this one here. Let me back out and come back to this here. If you notice, this bomb is now beginning to point downward, whereas this one is more horizontal, maybe it's even slightly nose up here. And that's due to wind resistance. And the only reason why this is happening here, the shape of it and the fins of it here will start acting a little bit of wind resistance, and it starts causing it to start pointing downward. And eventually when it hits the ground, it will be pointing almost straight up and down. Actually, not quite, but pretty close to it. And because of wind resistance, the bomb will actually begin to slowly fall behind the airplane. And so if it wasn't for wind resistance, these bombs will be exploding directly underneath the airplane, but because of wind resistance here, they're going to fall a little bit further behind. And if you ever see some of the old World War II movies when they used to put a camera up here and they'd drop the bombs, you can look, they have the camera will be looking straight down onto the ground. And the explosions will be occurring directly or almost directly underneath the airplane. All right, and here's a picture. Again, it's just a kind of like a water hose shooting a stream of water. But again, if you notice, it's a parabolic curve. And that's because every single water droplet, here, this one here has a velocity vector here. Over here, this one here, the water droplets have this velocity vector. Over here, this one has this resulting velocity vector. Over here, they're going to have this one occurring. Now, as time goes on, there's a little bit of spray, and that's because of some internal bouncing around of the water droplets and also some of the wind resistance here. But over short distances here, it should be, a nearly perfect parabolic curve. And you'll see that in other things as well. If you look at a drinking fountain, and if you look at something like this here, and the reason why drinking fountains and water hoses tend to be kind of wavy here is because water also has surface tension to it, and it causes the water droplets to kind of undulate within the thing here, which kind of gives like a rippling effect to the water. And so you would have, all these different kind of beads of water. They're somewhat trying to act independently, but due to surface tension, they kind of hold themselves together here, and you kind of get this undulation here. But again, technically, every single water droplet or every single water molecule within this is all trying to follow a parabolic curve. And even something like this here, even though it drops down much further here, this is still a parabolic curve. or if you go to some of these water fountain type of places here. Now, the reason why these tend to look a lot smoother is they actually send the water through a very long, narrow, skinny tubes, kind of like so here. And so as the water shoots through here, it takes out a lot of the ripples. So by the time it leaves the water here, they're all traveling parallel to each other. And so every droplet would be following the same path here. And if you ever see me do the demonstration where I throw a deck of cards, where I can throw an entire deck of cards without them separating almost across the room or over some large distance here, there's a technique to that where every card in a deck, come on now. So let's say this is stacked cards in a deck. Every single card is following its own parabolic curve, independent of the other one. And if you throw it just right, you can actually throw a whole deck of cards without rubber band or without the box over a large distance, and they will not separate. So fingers crossed, maybe in 3 weeks I can show you guys how that's done, or I'll try and make a video of it or something. Okay. And now even if you have like an irregular shaped object, for example, if you throw a hammer in the air, the same thing happens with this. But the thing is you have to follow, it's the center of gravity that follows a parabolic curve. So the center of gravity of a hammer is right about here. And so the center of gravity follows the parabolic curve. Now, if you try to look at something like the handle, this is going to do something kind of like strange like this, or even the head of the hammer will kind of do something kind of weird. If you follow the center of gravity, it's actually the center of gravity follows a parabolic curve. So the same thing is also true with a gymnast or a diver, is that someone jumping off of a diving board, it's their center of gravity that follows a parabolic curve. Their body is able to twist and contort themselves in any different types of directions here, and they are able to do spins and twists, but their center of gravity only follows a parabolic curve. So when you see like high divers and gymnasts doing all sorts of type of stuff here, if you follow their center of gravity, it only follows a parabolic curve. The rest of the body is doing other things around that center of gravity, but their overall motion is actually quite predictable. Okay, and here's a picture where someone threw what I believe to be a baseball bat with some reflectors or strobe lights attached to it. And this marker right here, I believe, is pretty close to being center of gravity, but I don't think he got it quite right here. But he also has one right here, another one here on the end. But if you look at the center of gravity part of it, it's not quite right here, but it's following basically a parabola here. But if you look at the end of the baseball, it kind of does these weird undulations here, or even for the parts further up here, it's kind of following this kind of weird pattern here. Okay. Now, something else with the projectiles, and especially for those who do any type of target shooting here or hunting or anything of that sort, is that if you're shooting over any large distance, the gun, if you're looking through the scope here, will have like these low lines. And see if I can try to draw something out here. So if you're looking, come on now, if you're looking through the scope of a gun here, you might see a line like this, and then you'll see these lines going across here, and they'll have like little markings on here. If you're trying to shoot for 50 yards, 100 yards, 150 yards here, you'll have these different increments on here that, if you have, you're trying to hit something, a certain distance here, and if you know the distance of it here, you want to line that marker up to, say this dot right here is your target that you're trying to shoot at. You're trying to line that marker up to that line if you know what the distance of it is, and that should allow you to be able to hit the target. Now, if it's either further or closer away here, you would have to line up to one of these other markers here. And So what you'll see here is that, if it's kind of like assuming that you're shooting on the ground and your target's on the ground. So if it's, don't ever do this here, but if you're shooting on the ground, your target's 0 meters, you don't have to aim at all here. Let's say, and this is if the gun is able to shoot at 100 meters per second. So if my target is 200 meters away, I'm sorry, if it's about roughly 200 meters away, I'm going to have to shoot just a little bit above 5 degrees in order for it to travel 200 meters. And so if I want my target is 400 meters away, I'm going to have to shoot about 12 degrees above the horizontal. So in other words, if this is my gun here, and I'm going to have to aim it up at a 12-degree angle, this angle right here, 12 degrees from the horizontal, in order to hit a target at 200 meters. So that means when the projectile leaves, has a 12-degree angle above the horizontal. So this is 100 meters per second, 12 degrees above the horizontal. I should be able to hit something 400 meters away. Now, look at this though. As you start getting further and further away, and so if I want to hit a target at 1,000 meters, I'm going to have to aim a little bit above 40 degrees here, about 43, 42, 43 degrees. And if I go a little bit beyond that, I'm getting close to 45 degrees. The maximum range is a little over 1,000 meters, not by much here, but a little over 1,000 meters. Now, if I try to go above 45 degrees, something weird begins to happen, is that this would actually begin to creep back down, all the way back down to 0. In other words, and to the ultimate end here, if I were to shoot at a 90-degree angle, guess what my range would be? 0, which means that's because it's going up and it's coming right back down. That's not a good thing. Please don't ever do that, okay? So, and that's what I'm trying to show here, is that, if you're able to hit a target aiming the gun at a 10-degree angle, and I hit the target right here. But also look at this. If I aim the gun at an 80-degree angle, I'll hit the same target. My range, my horizontal distance will still be the same. If I aim at a 20-degree angle, I'll say I hit the target right here. I can also hit the target by shooting at 70 degrees. And again, if I shoot at 30 degrees, I can, the projectile will travel this path here, hit my target, but I can also get the same result if I were to shoot upward at a 60-degree angle and hit the same target. But again, if I get to 45, I cannot go any further here. But if you notice anything kind of unique about this? Anyone? Did I see a hand up back there? Yeah, that's right. In other words, to hit this target, 10 or 80 degrees. Hit this target, 20 and 70. Hit this target, 30 and 60. They always add up to be 90 degrees. So the reason why 45 is the best one here is because 45 and 45 is going to be 90. So that is the reason why on the previous graph, at a 45-degree angle, that is the maximum angle that you can achieve here. If I were to extend this graph up to a higher value, up going top here, so start going into 50 and 60, I would have the same graph, but then kind of take this and make a mirror image this way, will curve upward like this, and ultimately going back to 0 again, or basically it will begin to slip back to what it was before. Okay, so that's the reason why at a 45-degree angle, if you want maximum range, you should shoot or throw at a 45-degree angle. Now, what is the advantage of knowing that I can hit a target at 20 or 70 degrees? And part of the reason is that if you have, let's say, a battle here or something like that, and you have an obstacle right here, if I try to shoot at a 20-degree angle, what's going to happen here is my projectile is going to hit the obstacle, say like a building or something like that. If my target is right here, X marks the spot, and I want to be able to hit it, but there's an obstacle here, what I can do is also get the same result by shooting at a 70-degree angle at the same velocity. I will still be able to hit the target at the same location here. So at the same velocity, at two different angles, you're able to hit the same thing here. Now the only one where that would not happen is at a 45-degree angle. Because if I have an angle or an obstacle right here, and I want to try to shoot for here, there's nothing I can do. It's going to hit the obstacle no matter what. This is actually what some of the very first computer was designed to do, was to come up with a table of, you want to target at a certain distance here, what angle, and how much basically gunpowder which you have to add in order for the projectile to travel that distance here. And so when they're trying to shoot artillery, the very first computer was actually designed to basically create this type of chart. So that way, in the middle of the battlefield, target's this far away. I need, it has a certain, I want to be able to travel a certain range. What angle do you have to put the gun at? And basically, how much explosives do you have to, or how much gunpowder you have to add to it to change this velocity in order to hit your target. So a little history here. Hey, guess what? Some videos. Actually, what I think I'm going to do is post some of these online, and I'll have you guys watch it, and I'll even have like an activity for you guys to do with that. All right, let's get into some examples here. What I'm going to do is I'm going to present the problem, and I will get it partially set up, and then what I want you to do is work it out, and you will see like a multiple choice, and I want you to work it out, put in your answer, and then give me the answer here. Once you put in the answer, it'll let you know whether or not you got it correct, and then if you continue playing after that point, I will show you the solution. So let's start off with this one. A ball is thrown horizontally at a velocity of 10 meters per second from a 100-meter cliff. How far from the cliff will the ball land? How fast will the ball be traveling vertically? Okay, so what I'm going to do is I'm going to set this up, and then I'm going to, a little bit later on, I'm going to have you solve for it, and then later on, after that, I'll show you how to go about solving for this, just so you can see how to go about solving for this. Now keep in mind too, there might be more than one way to actually solve this type of problem. All right, so in the story, we have a cliff that's 100 meters tall. The projectile is traveling 10 meters per second. And if you shoot it vertically from the cliff, two things we're trying to find out is what is its horizontal displacement, so that's the distance in the x direction, and also when it lands, what is its vertical velocity, basically what is its final velocity, which is technically in the y direction of it. Alright, now the key to solving a projectile is you need to separate the x from the y. Okay, so we have to look at what are the givens in the x direction and what are the givens in the y direction. So I'll write the givens up here. And for the x direction, so what do we know? Well, horizontally, this is traveling in the x direction, so the velocity, I'm going to put sub x here, is going to be 10 meters per second. Is there anything else that's acting in the x? Well, we don't know this value, but ultimately we want to solve for what is the range of the ball here. Okay, so that's an unknown. And is there anything else in the x? Well, if you remember, with a projectile, as it's moving horizontally, it moves at a constant velocity. So one thing we're also will be needing here is time. And time is a scalar unit. The time does not matter whether you're traveling horizontally, vertically, diagonally, circles, what doesn't matter here. Time is time. Okay, so it's always marching forward here. Then all the variables in the y direction. So now the x direction is 10 meters per second, but vertically, what's the initial velocity? The initial velocity in the y direction is 0. And if you ignore this part of it, it'll be the same as dropping a ball straight down. Okay, is there anything else we know? Well, the distance here is in the y direction, so the distance in the y direction here is 100 meters. Now, is there anything else? Yeah, gravity. So the acceleration of gravity is 9.8 meters per second squared. Okay, is there anything else? Well, when you don't know, basically just solve for everything. So we know the initial velocity. Ultimately, well, the one thing we do have to solve for is this final velocity, which is acting in the y direction, which is unknown. Is there anything else? Now, if you look at this, we have its initial velocity, its final velocity, its distance, the acceleration. Really, the only variable it's missing is time. So I'm also going to solve for time here as well. Now, the time for it to fall down is also the time for it to move across. And those two times, these two times here, are going to be one and the same. I apologize if you hear the dog barking in the background here. So, alright, so if you look at this in the x direction, we don't have enough information. We have two unknowns here. If you look at the y direction, we actually have enough information that we can go ahead and maybe start solving for it. But it might be easier too to also look at what are the formulas that we can use in the x and y direction. So for the x direction, for the formulas that we can use here, we can use, really there's only one formula. Velocity is equal to distance over time. That's it. Okay? So we have the velocity, we don't have the distance, we don't have the time. If you look at these over here, if you remember your three main formulas for the acceleration, you have Vf is equal to Vi plus At. We also have Vf is equal to the square root Vi squared plus 2Ad. And also we have d is equal to Vit plus 1/2 At squared. Okay, so I'm going to give you this information here, and what I'd like for you to do is go ahead and work this out. The one hint I can give to you here is, in this situation, and almost most projectile problems here, you almost always have to solve for the y before you solve for the x. Okay? So treat this as though you're dropping a ball straight down from 100 meters. How much time will it take for it to fall down? Okay? Once you know that time, and also in the meantime, you go ahead and solve for how fast is it moving vertically downward. So you can go ahead and solve those two things. You can actually solve for these two things here. By the time here that it falls down, it's also moving horizontally at a constant velocity. So if you know that time, you can rearrange this and solve for the distance, but this would be the distance in the x direction. So technically, this is the velocity in the x direction and the distance in the x direction. All of these are everything happening in the y direction. So what I'd like for you to do is work this one out and answer the question. And then after you answer the question, then we'll go through and look at this problem being worked out. Good luck. All right, well, hopefully you got the the choice correct, but if not, let me go ahead and work this one out. And also, the way that I may have worked it out may be a little bit different than the way that you worked it out. And one thing with these type of problems here, there can be more than one way to solve for these type of problems here. So first thing I'm going to do is I'm going to go ahead and solve for the time. Alright, so if you look at the choices here, we have the initial velocity, we have the distance in the y direction, we have the acceleration, and we don't know time. Well, if you look at all the choices here, we have distance, we have the initial velocity, we don't know the time, we do know the acceleration. Alright, so the equation we'll have to use here is this last one here, d is equal to vit plus 1 half at squared. So I'm going to work this one out. So d is equal to vit plus 1 half at squared. Well, since the initial velocity is 0, we can ignore that part. That way you don't have to use quadratic equation, unless you really like to use it. So d is equal to 1 half at squared. But we need to solve for time. So I need to get rid of the 1 half, so I need to multiply both sides by 2. That way 2 and 1 half will cancel out. End up with 2d is equal to at squared. Then I need to divide out the a. These two cancel out. And then 2 squared is equal to 2d all over a. And then get rid of the square. I need to take the square root. These two will cancel out. So time is equal to the square root of 2 times the distance all over the acceleration. So let's plug in the numbers. Time is equal to the square root of 2 times the distance. The distance is 100 meters. And divided by the acceleration, well, it's falling, 9.8 meters per second squared. And if you work this out, you should get an answer of 4.517 seconds or thereabouts. Okay, so one thing I would recommend doing here in the problem is put in your answer, 4.517 seconds, which is also the amount of time for it to move across horizontally. Alright, so now we have the time. So we know here that the ball that hit the ground, whether it's being dropped or being shot off at 10 meters per second, it could be 100 meters per second, no matter what, ignoring wind resistance, it will hit the ground at a time 4.517 seconds. Okay. So let's go ahead and solve for the velocity, the final velocity. Now this is the velocity right before impact. Don't say 0 because otherwise here it's 0, here it's 0, which will mean it didn't move. But this is the moment before impact. So now you could actually either use the first equation here or even the second equation. Now if we're using the first equation, we're going to be using the answer that we got down here. And ideally, don't try to use a value that you've already calculated, just to kind of keep the accuracy a little bit higher here. So I'm going to be using the middle equation here. So let's work this one out. Now, because the equation, we don't have to rearrange it. So df is equal to the square root vi squared plus 2ad. And since the initial velocity is 0, we can ignore that and simplify it a little bit. V is equal to the square root of 2ad. So now, let's plug in the numbers. The velocity is equal to square root of 2 times the acceleration, which is 9.8 meters per second squared, times the distance. Well, is traveling 100 meters. And when you end up getting this here, you end up getting 44.272 meters per second. Now, if you end up getting a really large number, chances are what you forgot to do was take the square root of that answer. That's a common mistake here. A lot of people overlook the square root here. So if you end up getting a really big number here, that's probably what happened. Okay, now you could also have done the same thing with using the first equation here, and let me just do that here real quickly. So BF is equal to BI plus AT, and since the initial velocity is 0, we can ignore that. So we have 9.8 meters per second squared and a time of 4.517 seconds. So the final velocity, according to these values here, are 44.267 meters per second. And as you can see here, it's pretty close. Okay, and this is the reason why is because this time was rounded here, which kind of throws the accuracy of this value off here. So that means when this projectile ended up hitting the ground, it was traveling at 44.267 meters per second. Now I'm going to come back to that here in a little bit. So I'm going to put my answer up here. It's 44.267 meters per second, if you can see that. Okay, make sure you, when you're doing these, always show the units. Okay. Now, the last part. If it took 4.517 seconds for it to fall straight down, that also meant it took 4.517 seconds for it to go across horizontally. So, because the horizontal velocity is at a constant rate, all we really have to use is this form right here. So now, for the last part of it, to solve for the range, velocity is equal to distance over time. Now I'm looking at the velocity in the x direction, and I'm solving for the distance in the x direction. You can't cross x and y, okay? So everything, you have to separate everything in the x from everything from the y. I need to solve for the distance in the x direction. So the distance is equal to the velocity in the x direction times time. So I'm going to plug in the values. So the velocity in the x direction was 10 meters per second, and it's traveling, I'm not sure if I can squeeze it in here, 4.517 seconds. Okay, seconds will cancel out. We're not use a calculator on this one here. And we end up getting a value of 45.17 meters. Okay, so this is how far. So this would have traveled 45.17 meters horizontally. So it would have dropped 100 meters. It would travel at 45.17 meters if you have a projectile being shot horizontally at 10 meters per second. And it will take 4.517 seconds for it to hit the ground. Now, I was saying something here with this part here, is that as the ball is falling down, if you remember, vectorally speaking, the path is always a parabola. And the parabola, the arc of its parabola, is a resultant between its vertical velocity and its horizontal velocity. Now, this is not drawn to scale, obviously, here. But let me just point out something here, is that the fact that the projectile is going 10 meters per second horizontally, and also going something a little closer to scale here, 44.267 meters per second vertically. That means at the point of impact, vertically it's traveling this fast. Horizontally it's still traveling 10 meters per second. But the velocity it's actually traveling is a resultant of those two. So at that point in time, even though the problem didn't ask for it here, I want to point this out because one of the other problems it does ask for something like this is what is the resulting velocity? Okay, so go ahead and give me the answer for that one, even though the question didn't ask for it on the video here on the slides. What is the resulting velocity, and also what angle is it traveling vertically at the point of contact? Okay, so go ahead and work that one out and select your answer, and then I'll go ahead and show you how to go about solving for this one. Alright, so hopefully you did well on that question. So let's go ahead and solve this one here. Alright, so actually I made a mistake. It's a slight error here. The initial answer we got down here, 44.272 and then 44.267. I said 44.267. This up here, a little more accurate here, be 44.272 meters per second. Okay, if you use 44.267, that's fine too. And then I'm also going to make the same change over here. It's not going to matter that much, but we'll give it a try. Alright, so if you look at the diagram, so it's going 10 meters per second horizontally, it's going to 44.272 meters per second vertically. And what is the resulting velocity? Now, that is Pythagorean theorem. So to find the resulting velocity, hopefully you guys can see that here, is equal to the square root. This is your c squared is equal to a squared plus b squared. So so the resulting velocity is equal to the square root of 10 meters per second squared plus 44.272 meters per second. If you use the other one, that's fine. Make sure you square that. And then add those together, take the square root of that, and you end up getting an answer of, what was the answer here? 45.39 meters per second. So that means that the projectile is actually going, right before impact, is going 45.39 meters per second. But it's also going at a very slight angle. So find out what is this angle from the vertical of it. So this is your angle, this is your opposite, which is 10 meters per second, and this value here is 44.27, which is your adjacent. So opposite adjacent, SOHCAHTOA, you want to use tangent. So tangent theta is equal to opposite over adjacent, and tangent theta, my opposite, this is 10 meters per second, so this side here is also 10 meters per second. It's kind of confusing the way I have this right now here, I apologize. So the opposite is 10 meters per second, and the adjacent, this side right here, is 44.272. Okay, and we want to solve for theta, so we have to get rid of the tangent by taking the inverse tangent. So we're taking the inverse tangent of 10 meters per second over 44.272 meters per second. Now, make sure that you are in degree mode, not radian mode, because otherwise you might get a kind of a weird answer. And so you end up getting a value of about 12.73 degrees. So this angle is 12.73 degrees. So that means when this projectile It's falling to the ground. It had a velocity of 10 meters per second. Here it still had 10 meters per second. Here it was still 10 meters per second. When it hits the ground, or the moment before it hits the ground, it still had a velocity of 10 meters per second. Here it had no vertical velocity. Here it had a little bit, then a little bit more, and then right before it hits the ground, it had a velocity of 44.272 meters per second vertically. But the resultant of that is this, and obviously it's not drawn to scale, but the moment before it hit the ground here, this right here would have been tangent to the arc, the parabolic curve of its path. Now I don't have it drawn that way here because I didn't draw things accordingly here. And also at the moment before it hits the ground here, it would have been traveling at a slight angle of 12.73 degrees. Okay, hopefully you can see that here. So, hopefully you did well, and we'll take a look at the next problem here after a bit. Good job.